Okay, let's get started. Hi, my name is Gukchin Lei, who is working at reliability team in IMAC as a postdoc. Okay, today I will introduce the paper which is titled Multiple Machine Learning Approach to Characterize Two-Dimensional Nanoelectronic Devices through Featurization of Charge Fluctuations. So, to be honest, I use the applied machine learning and current fluctuation as a function of time. Okay, these are the content for this presentation, and I've mainly referred and studied lecture from Kevin and Ava. I've just studied a little bit about applied machine learning, not developing, and I will briefly introduce you guys to using already completed and developed machine learning algorithm. This is the outline of this paper. We use an applied machine learning, as I told you before, and current fluctuations, the sequential data, in order to characterize the nanoelectronic devices, especially into the layered materials FETs. So to begin and really motivate the need for processing the sequential data as a function of time, let's consider a very simple example. Suppose we have this basketball and we want to predict this basketball will travel next. However, if we don't have any prior information about the trajectory of this basketball or its history, any guess on its next location would be a random guess, right? But if in addition to this current location, if you have a bit of information of its previous locations, like this, the problem becomes much easier, right? And this is really kind of set up this idea of processing and handling sequential data. And you know, the sequential data is all around us. And I think the most popular and studied topic is sound wave and speech recognition, like this. For example, we can see a funny video about speech recognition. Okay, let's see that.
What's the buttons?
Oh no, they installed voice recognition technology in this lift. I heard about this.
Voice recognition technology in a lift in Scotland. You ever tried voice recognition technology?
No.
They don't do Scottish accents.
11.
Could you please repeat that?
11.
11.
You need to try an American accent. 11. 11.
That sounds Irish. You're American.
What doesn't it?
Where in America is it?
Yeah, we can see some funny video. As you saw, we can see many other sequential data which we can use for an applied machine learning, such as weather forecast and stock predictions like this. One day, we were suddenly just curious about operation principle of Siri in iPhone. So we read some books and lectures related to speech recognition and suddenly found that sequential data is very similar to the current fluctuation as a function of time we often saw like this. And please look, don't you think the sound wave data and current fluctuations look very similar to each other, right? That was the beginning of our journey of this paper. Fortunately, we had a lot of sequential data, the current fluctuation data measured from me and my colleagues in my lab, especially in my PhD in Korea University. A lot of measured data had been accumulated for decades. This graph shows the hype cycle from Gartner industry in AI, artificial intelligence. Cases of applying artificial intelligence are in the preparation stage of development, except for speech recognition and GPU accelerators. In addition, autonomous driving is currently in commercialization. I searched the frequency of articles and paper on the Web of Science, and it started to increase rapidly since 2015. And in 2019, more than 20,000 articles were published as well. Among them, papers containing nano, transistor, device, and sensor became to appear under the 7%. Before the experimental method, I'll introduce some theoretical backgrounds for this paper. Of course, I'm not an expert of the theoretical background of the machine learning, but I will I will introduce that very short and briefly. Okay, I'm pretty sure many of you already expert on this principle of Markov chain. The main point of the Markov chain is that of the probability of a single state depends on the previous state like this. And the hidden Markov model assumes that each state follows the Markov chain, but all is hidden. By example, let's say we are a climate researcher for 20 years ago, and all the given information and only given information is I'm sorry for that. Only given information is ice cream consumption records. Only with this consumption records, we want to know if the weather was hot or cold or warm at that time. We can see a chain of ice cream consumption records like this, but it is very difficult to directly see what the weather is for that day. The hidden Markov model tries to estimate the state behind observations. We need to characterize the data for machine learning, and normally it's called as data featurization. And in speech recognition, audio waves are featurized by mere frequency cepstral coefficient, MFCC. The MFCC mechanism can be explained and calculated through this whole sequence. First, we divide a frame we divide the frames and take the window for the original audio waves, like this. And then each divided frames Fourier transform into spectral densities, like this. And they filtered by Mel filter, and we can obtain the Mel spectrum. Finally, we can extract the coefficient by inverse Fourier transform by cosine Fourier transform, cosine inverse Fourier transform. So the reason we should use the AI approach for analyze is to improve the complexity and volume of input data by producing improved and optimized models. For using an applied machine learning, just in my opinion, we need this simple sequence like this. First of all, we need to check and select and pre-process our data. In this process, we must check how much missing data in our dataset, and then we should featureize and clean the data as well. And funny thing is, after this process, sometimes we can find that we don't need machine learning or deep learning at all. It's funny, right? But if we need an applied machine learning even after featureization and cleaning data, we should select the proper algorithm, and then we must choose object and proper evaluation and validation method. Yeah, finally, let me talk about the experimental part of this paper. First, I will introduce the featureization process of the current fluctuations and machine learning algorithm for learning these engineered features. Me and my colleagues fabricated a lot of 2D layered FETs and measured current of them as a function of time. And I think somebody asked me, why did I use current amplifier and DAQ for measuring current data like this? And the reason for that is I don't have enough money to buy some good equipment. So I'm very happy and experiencing a new world in iMac when I measure the devices using good equipment these days. And then we need feature engineering like this, normalization of current fluctuations and dividing data like sound waves and Fourier transform and filtering on Mel scale and discrete cosine transform, as I told you before, is inverse Fourier transform. Therefore, we finally trained with machine learning using this engineered data as shown in the figure below like this. And here we trained feature data using hidden Markov model to extract a square vector large Y and train them again with neural network to infer the device conditions or characters. So we use three machine learning algorithms. First, we only use the hidden Markov models from the score, and then we trained once more from the Y vector, the square vector, into the neural network models, and then we obtain the inferring the device conditions. So what do you think of this transfer curve? These transfer curves at the left top figure. Can you recognize the profile and condition of this device only in given transfer curves? Maybe you can do that with subthreshold swing, on current, or threshold voltage, and any parameters. However, the more data you have, the more difficult it will be to classify and analyze. So in this paper, we use current fluctuation data of each device and featureize as I told you in previous slides. The current fluctuations of each devices have their own trapped profile, and accordingly, spectral envelopes, I don't know how to pronounce, maybe spectral envelopes are extracted differently each other. Therefore, we finally obtained the engineered MFCC data for each own devices as below, like this. And please look at the engineered MFCC data from graphene and molybdenum disulfide on silicon dioxide and after e-beam radiation, and onto hexagonal boron nitride at 25 Kelvin, at 100 Kelvin, and 200 Kelvin. While it is difficult for us to analyze and classify thousands of these engineered MFCC data with our own eyes, but if we train using machine learning, we can characterize and classify the devices. So as I told you before, we use three kinds of machine learning and deep learning algorithms for interfering our devices. First, only use hidden Markov model from the score and score vectors and neural network. What I mean is combined hidden Markov model and the neural network, and then the convolutional neural network model. So we have three kind of machine learning algorithms. So the classification accuracies have three accuracies like this: the pink one and gray one and the blue one. So the classification accuracies and processing time obtained using hidden Markov model algorithm and the combined hidden Markov model and neural network model method like this. When the number of data was 7,800, the hidden Markov model classification accuracy was only 76%, with F1 score using full-forward under the 0.7 using full-forward close validation. For 22,000 data points, the hidden Markov, the combined models classification accuracy increased to 95% with F1 score of 0.93 and processing time of 11 hour, almost 11. No. Oh, this is for the hidden Markov. Almost 13 hour. Oh, no, 11 hours. Sorry for that. 11 hours for each full close validation. However, for 48,000 data points, classification accuracies exhibit no further improvement like this, and the only processing time increased to almost 15 hours. As you can see on the right figure, almost every conditions the labels have over the 80% accuracies, but only two labels have very awful accuracies. Interestingly, those two labels have very large contact resistance like this. So as you can see in the confusion matrix, they confuse each other. And I was thinking about what can we do in the future? If we have enough number of images of something, such as before and after WTI or hot carrier degradation of SEM or TM images, I think we can figure out the degradation pattern or analyzing some data, analyzing pattern using image classification of deep learning process. In addition, if we have a lot of complicated data such as current voltage or capacitance or impedance or current fluctuation as a function of time data, I think we can explain with an optimized model through machine learning or deep learning training. Okay, thank you for your attention. Bye.